Hello everyone, this is a audio recorded lecture on the topic thermochemistry. The learning outcomes of thermochemistry are interconvert energy units, distinguish between the system and the surroundings in thermodynamics, calculate internal energy from heat and work and state sign convention of these quantities, explain the concept of a function and give examples, calculate del H from del E and P del V. Relate QP to del H and indicate how the signs of Q and del H are related to whether a process is exothermic or endothermic. Use thermochemical equation to relate the amount of heat energy transferred in reactions at constant pressure at the amount of substance involved in the reaction. Let's start. Energy is the ability to do work or transfer heat. Thermodynamics is the study of energy and its transformation. Thermochemistry is the study of chemical reaction and heat energy changes that involve heat. Heat and what is heat? Energy used to cause the temperature of an object to increase, and work, energy used to cause an object that has mass to move. Next, electrostatic potential energy. The most important form of potential energy is molecules in electrostatic potential energy. Electron charge 1.602 into 10 raised to power minus 19 coulomb. The unit of energy commonly used is the joule. Attraction between ions. Electrostatic attraction occurs between oppositely charged ions. Energy is released when chemical bonds are formed. Energy is consumed when chemical bonds are broken. First law of thermodynamics. Energy can be converted from one form to another, but it is neither created nor destroyed. Energy can be transferred between the system and surrounding. Chemical energy is converted to heat in grills. Sunlight is converted to chemical energy in green plants. There are many examples of conversion of energy from one form to another. Next is system and surroundings. The system includes the molecules of interest. The surroundings are everything else. In thermochemistry, we study the exchange of energy between the system and surrounding. Types of system. Open system. In open system, matter and energy can be exchanged with the surroundings. In closed system, exchange of energy takes place, but exchange of matter does not take place with the surrounding. In isolated system, neither matter nor energy may be exchanged with the surroundings. Next is internal energy. The internal energy of a system is the sum of all kinetic and potential energies of all components of the system. We call it E. Del E is equal to E final minus E initial. This is the graph shown between internal energy and initial state of a system. Energy lost to surroundings. Internal energy of system decrease del E negative. Energy gained from surroundings. Internal energy of system increases यानी कि del E positive. By definition, the change in internal energy del E is the final energy of the system minus the initial energy of the system. That is, del E is equal to E final minus E initial. If del E is less than 0, then E final will be less than E initial. The system released energy to the surroundings. Thermodynamics quantities. First, a number, unit and sign. A positive del E result when the system gains energy from the surroundings. A negative del E results when the system loses energy to the surroundings. For Q, positive means system gain heat, negative means system loses heat. For W, positive means work done on system, negative means work done by system. For del E means net gain of energy by system, negative means net loss of energy by system. When energy is exchanged between the system and the surrounding, it is exchanged at either heat Q or work W, that is, del E is equal to Q plus W. Exchange of heat between system and surrounding. When heat is absorbed by the system from the surrounding, the process is endothermic. When heat is released by the system into the surroundings, the process is exothermic. State function. The internal energy of a system is independent of the path by which the system achieved that state. Internal energy E is a state function. Q and W are not state function. Del E is the same whether the battery is shorted out or is discharged by running the fan. Minus Q plus W are different in two cases. Next is work. This is the diagram shown to explain work, in which a vessel is taken from which zinc solid is passing. Then it is get discharged in HCl aqueous. It also has a piston and a H2 gas plus original atmosphere, where Zn solid plus 2H positive gives Zn2 positive plus hydrogen gas. Next is enthalpy. Enthalpy is a thermodynamic function equal to the internal energy plus pressure into volume, that is H is equal to E plus PV. When the system changes at constant pressure, the change in enthalpy del H is equal to del into E plus PV. This can be written del H is equal to del E plus P del V. Since del E is equal to Q plus W and W is equal to minus P del V, we can substitute these into the enthalpy expression, from where del H is equal to Q. The enthalpy change del H is defined as the heat gained or lost by the system under constant pressure. Del H is equal to Qp. Properties of enthalpy. Enthalpy is a state function. Enthalpy is an extensive property. Enthalpy is reversible. The enthalpy change for a reaction is equal in magnitude but opposite in sign to del H for the reverse reaction. Del H for a reaction depends on the state of the product and the state of the reactants. Endothermic and exothermic. A process is endothermic when del H is positive. A process is exothermic when del H is negative. Enthalpies of reaction. This quantity del H is called the enthalpy of reaction or the heat of reaction. A thermochemical equation is an equation for which del H is given. For example, 2 moles of hydrogen plus oxygen gives 2 moles of water, and hydrogen plus half mole of oxygen also gives 1 mole of water. In both the cases, del H is different. In first case, del H is equal to minus 483.6 kilojoule, and in second case, del H is equal to minus 241.8 kilojoule. The enthalpy changes assumes the coefficients are moles of the substance. Next is calorimeter. Calorimeter, the measurement of heat released or absorbed by a chemical reaction. A calorimeter is the device used to measure heat. The quantity of heat transferred by the reaction causes a change in temperature of the solution. Heat capacity and specific heat. The amount of energy required to raise the temperature of a substance by 1 Kelvin is called its heat capacity. The units of heat capacity is joule per kilo. Joule per Kelvin, We define specific heat capacity as the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. If the amount is 1 mole, it is molar heat capacity. Constant pressure calorimeter. Indirectly measure the heat change for the system. Because the specific heat for water is well known, that is 4.184 joule, we can measure Q for the reaction with this equation. Q of the solution is equal to Cs into m into del T is equal to minus Q of reaction. The calorimeter and its contents are the surroundings, so Q solution is formed from the mass, heat capacity and temperature changes. Now these are some example givens for practice. There are also some examples. Next is bomb calorimeter. Because of the volume in the bomb calorimeter is constant, what is measured is really the change in internal energy, del E, not del H. For most reactions, the difference is small. The heat absorbed by water is a very good approximation of the enthalpy change for the reaction. Now, next is Hess law. Del H is known for many reactions, but it is inconvenient to measure del H for every reaction in which we are interested. However, we can calculate del H using published del H values and the properties of enthalpy. Hess law states that if a reaction is carried out in a series of steps, del H for the overall reaction will be equal to the sum of the enthalpy change for the individual step. Means del H is a state function. Most del H values are labeled del H node and measured under standard conditions, that is at 1 atm pressure, 298 Kelvin temperature and 1 mole concentration. Using Hess law, when two or more thermochemical equations are added, the enthalpy change of the resulting equation is the sum of those for the added equation. This is the example given, and there are some more examples for Hess law. Next is enthalpies of formation. An enthalpy of formation del HF is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental form. Standard enthalpy of formation. Only one enthalpy value is needed for each substance, called the standard enthalpy of formation. The standard enthalpy of formation is the enthalpy change when 1 mole of a substance in its standard state is formed from the most stable form of the element in their standard states. Next is standard states. Enthalpy changes depend on the temperature and pressure at which they are measured. When applying Hess law, all values must refer to the same condition of pressure and temperature. The standard state of a function at a specified temperature is the pure form at 1 atm pressure. Standard enthalpy of formation. The symbol used for standard enthalpy of formation is del HF node, where the node designates standard state. The product is always 1 mole of a single substance. The standard enthalpy of formation of the element in their most stable form is 0. Some example of standard enthalpy of formations are given below. Next is enthalpy of reaction. Imagine this as there is a reaction given C3H8 plus 5O2 gives 3 moles of CO2 plus 4 moles of water. Imagine this as occurring in 3 steps. First is C3H8 gives 3 moles of carbon plus 4 moles of hydrogen. Next is C3H8 gives 3 moles of carbon plus 4 mole of hydrogen. Now 3 mole of carbon plus 3 mole of oxygen gives 3 mole of CO2. And 4 moles of hydrogen plus 2 moles of oxygen gives 4 moles of H2O. The sum of these equations is C3H8 plus 5O2 gives 3 moles of CO2 plus 4 moles of H2O. This is the whole process for these 3 steps. And for the calculation of enthalpy of formation. Now, on the behalf of the above example, some other examples are given for the practice. Next is bond enthalpy. The enthalpy associated with breaking 1 mole of a particular bond in a gaseous substance is called bond enthalpy. Bond enthalpy is always positive because energy is required to break chemical bonds. Energy is released when a bond forms between gaseous fragments. The greater the bond enthalpy, the stronger the bond. Bond enthalpies and enthalpy of reaction. To obtain an estimate of del H, sum the bond enthalpies for all bonds broken and subtract the sum of the bond enthalpies of all bond forms. Del H of reaction is equal to bond enthalpy of bond broken minus bond enthalpies of bond formed. Predict whether a chemical reaction will be endothermic or exothermic using bond enthalpies. Next is energy in food. The energy released when 1 gram of food is combusted is its fuel value. Now this is the table for composition and fuel values of some common food like carbohydrate, fat, protein, apis, beer, bread, cheese, eggs, fudge, green beans, hamburger, milk, peanuts, etc. Most of the energy in food come from carbohydrate, fat and protein. Protein produce 17 kilojoule per gram, same as carbohydrate. However, their chemical reaction in the body is not the same as in calorimeter. Now this is the table given for fuel values and composition of some common fuels like wood, anthracite coal, bituminous coal, charcoal, crude oil, gasoline, natural gas and hydrogen. So this is all in this video. Thank you for watching this.